In this video, I'll be solving 15 circuit problems, and they're going to help you understand circuits better. When those questions appear in your finals, you're going to smash them and grab a 7. Each of the 9 resistors has resistance R. The total resistance of the arrangement shown is 24 ohms. What is R? In order to solve this, let's figure out the resistance of this block. We must note that the 3 resistors are in parallel, so the total resistance of this combination would be 1 over R plus 1 over R plus 1 over R. And that gives us that the total resistance is R over 3. So that's the resistance of this block. The resistance of this parallel block is going to be the same, R over 3. And it's going to be the same for this one. In other words, we have R over 3, R over 3, and R over 3. All 3 of them are connected in series. That means the total resistance would be, the total equivalent resistance is 3 times R over 3. That is simply R. And since the total resistance is 24 ohms, we get R is equal to 24 ohms. And that solves the first problem. If you need more help, I also teach one-on-one. I'll put the link in the comments below. A wire has resistance R. The wire is cut into 2 pieces of equal length. The 2 pieces are connected in parallel. What's the resistance of the parallel combination? So we have a wire that has resistance R. If we break it into 2 parts, each piece will have a resistance of R over 2. So these 2 pieces have resistance R over 2 and are connected in parallel. So this is R over 2 and this is R over 2. If we are supposed to find the total resistance of the parallel combination, we do 1 over R total equals 1 over R over 2 plus 1 over R over 2. That is equal to 2 over R over 2, that is 4 over R. In other words, the total resistance would be R over 4. And that's the first option, and we are done with this question. A cylindrical conductor X has resistance R. X is melted and all the material is used to make another cylindrical conductor Y. Double the length. What's the resistance of Y? So we have a cylindrical conductor. If this is the conductor, conductor X, its resistance is R. And if we melt it and make another cylindrical conductor that has double the length, that is this, its cross-sectional area has to decrease by half. So if the cross-sectional area here is A, it has to be A over 2 in this case. If the length is L, the length in this case is 2L. Why should the cross-sectional area decrease by half? So that the volume stays constant. Okay, if we focus on resistor X, we can write resistance X equals resistivity length over area. If I find the resistance of Y, I would write resistance of Y is resistivity length over area. This turns out to be 4 times rho L over A. But rho L over A is resistance R. That means resistance Y is 4 times the resistance of X. So the option is C. 3 identical resistors, each of resistance 6 ohm, are connected together. Which of the following is not a possible value of the total resistance of the connected resistors? So we have 3 identical resistors. What if I connect all 3 of them in series? If I do that, the total resistance would be 18 ohms. What if I connect 2 of them in series and 1 in parallel? What would the resistance be? Well, the total resistance of the top branch would be 12 ohms and of the lower branch is 6 ohms. So, and they are in parallel. So the total resistance would be 1 over 12 plus 1 over 6, that is 3 over 12. That means R will be 4 ohms. So 18 ohms is possible, 4 ohms is possible. What if I keep 2 in parallel and 1 in series? So I have 2 resistors, they are in parallel, connected in series with a third one. What's the resistance of this combination? So this is 6 ohms and 6 ohms, and this is a parallel combination. The equivalent resistance is going to be 3 ohms. Then that 3 ohm is in series with this 6 ohms, and that gives me a value of 9 ohms. Alright, what if I connect all three of them in parallel? If I do that, I have a 6 ohm, another 6 ohm, another 6 ohm, and all three of them are in parallel. The equivalent resistance would be 1 over 6 plus 1 over 6 plus 1 over 6. That means the resistance would be 2 ohm. So if we look here, 2 ohms is possible, 9 ohms is possible, 4 ohms is possible, 18 ohms is possible. So 2, 4, 9 are possible, 12 is not possible, so that is the right option, is larger. In the circuit shown, what changes to the resistance will definitely result in an increase in the reading of the voltmeter. In other words, we want the voltage across the first resistor to increase. How do we do that? Well, Ohm's law says the potential drop equals current times resistance. So you can vary either I or you could vary R. Now if I decrease the value of R2, the resistance in the entire circuit is going to decrease. That means the current is going to increase. Therefore, the current increases and the voltage across the resistor R1 increases. So the first option would be R2 must decrease. We could also increase the value of resistance R1. If R1 goes up, the voltage across will also go up. So the other option is R1 must increase, and that's option B. R1 increases and R2 decreases. Next up, the resistors have resistances R1 as 50 kilo ohms and R2 as 10 kilo ohms. The voltmeter is ideal and the internal resistance of the cell is negligible. And we have to find the reading of the voltmeter. We begin by noting that the total resistance of the circuit is 60 kilo ohms. That means the current in the circuit I would be 12 divided by 60 kilo ohms. That means the voltage drop across R1 would be I, current, times the resistance R1. Current is 12 over 60 kilo ohms, and the resistance R1 is 50 kilo ohms. Kilo ohms goes away with kilo ohms, and if we solve this, we end up with 10 volts. Three identical resistors are connected as shown. The cell has no internal resistance. Resistor R burns out. What happens to the current in X and the current in Y? Let's say the resistance of each section is R. Then the resistance of this parallel combination is R over 2. And it's in series with the Y resistor. So the total resistance is R over 2 plus R, that is 3R over 2. That means the current that's going to flow out of the cell is going to be E over 3R over 2, that is 2E over 3R. That's the current that's flowing out of the cell. Now that would be the current that would flow through Y, and the current through X is going to be half of that. So if this is I, this is going to be I over 2, and this is going to be I, where I, the current, is given by this equation, 2E over 3R. Now let's say the resistor Z burns out. What happens then? Well, if the resistor Z goes away, let's put a tape here, then that portion is disconnected. If that's the case, the total resistance of the circuit becomes 2R. 2R is the new resistance. That means the new current I prime would be E over 2R. Now I prime is smaller than I. That means the new current is less than the initial current. Therefore, the current through Y has decreased. But what about the current through X? We must remember that the current through X was 2E over 3R divided by 2, half of the current, which is E over 3R. That is the previous current. the new current is E over 2R. That means the new current is larger than the previous current through X. So the current in X has increased, while as the current in Y has decreased. Right, this is our final question for today. The source in the circuit has EMF 40 volts and the internal resistance is 10 ohms. XY is a uniform wire of resistance 90 ohms and external resistor 45 ohms is connected as shown. What's the minimum reading of the ammeter and the maximum reading of the voltmeter as the slider moves from X to Y? First of all, we would want to find the minimum reading that the ammeter could have. In order to have the minimum possible value, the resistance in the circuit has to be maximum. Now if we place these two in parallel, 45 ohm and the rod in parallel, the resistance is going to decrease. We don't want that to happen. So what we do is we take the slider and place it all the way here. That means the entire rod XY is isolated and there is no current flowing through the 45 ohm resistor. In that case, what would be the current? Well, the resistance would be 10 ohms due to the internal resistance and 90 ohms due to the rod. That means the total resistance in the circuit is 100 ohms. The voltage is 40 volts. Therefore, the current would be 0.4 ampere. This gives us the minimum reading the ammeter can have. If you take the slider and place it anywhere else, the ammeter will show a larger reading because this resistor and the rod will become in parallel. And when they are in parallel, the resistance decreases. If resistance decreases, the current will increase. Now at the minimum reading of the ammeter, all the current flows through the upper terminal. That means there is no current flowing through the 45 ohm resistor. If there is no current through the 45 ohm resistor, the voltage across it will be 0 volts. So the voltmeter would measure 0 volts. In order to increase its reading, we would take the slider and push it all the way over here. If that's the case, then this 90 ohm resistance would be in parallel with the 45 ohm resistor. What would be the total resistance of these two? The rod and the external resistor, we can find it 1 over R equals 1 over 90 plus 1 over 45, that is 3 over 90. That means the resistance of the parallel combination is 30 ohms. Alright, now this 30 ohm is in series with the 10 ohm here, so the total resistance is 40 ohms. Now if the total resistance is 40 ohms and the voltage is 40 volts, current has to be 1 ampere. Alright, if the current is 1 ampere, that 1 ampere flows through this and enters this end of the circuit. What's the voltage across this resistor? It would be current, which is 1 ampere times the resistance, which is 10 ohms. That gives us 10 volts. So there's a potential drop of 10 volts across this. Therefore, there must be a voltage drop of 30 volts across this set because the total has to be 40. That means the voltmeter is going to measure 30 volts, and that's the maximum reading it can have. And that completes 15 problems for today. I also teach one-on-one. If you need more help, I'll put the link in the comments below. I'll see you in the next one. Happy learning.